So we're going to take a look at carbohydrates, and this is really the first transition that we're making from looking at specific functional groups to really starting to explore metabolites. So a metabolite is something that is found within living organisms. It's a molecule that is a component of metabolism. And so the first metabolite or primary metabolite that we're going to be looking at are carbohydrates. So there are two general classifications that we think of in terms of carbohydrates, and those are going to be simple and complex carbohydrates. Simple carbohydrates are made up of monosaccharides and disaccharides. If we think about that word mono and di, that would suggest one sugar and two sugar. Some examples of monosaccharides and disaccharides are shown. These would be glucose, fructose, galactose. For disaccharides, that would be maltose, lactose, and sucrose. And then if we think about complex carbohydrates, these are polysaccharides. And these polysaccharides are poly, so many sugars. And examples of these types of polymers that are carbohydrates would be starches, fibers, and glycogen. So when we think about a carbohydrate, what are we really talking about chemically? So this is a polyhydroxy, so multiple alcohol functional groups, and an aldehyde. Or a polyhydroxy ketone, multiple hydroxyl groups and a ketone, or some type of substance that's going to give these compounds if hydrolysis, or the addition of water as a mechanism, is included. So what is a monosaccharide then? So a monosaccharide is a carbohydrate that cannot be hydrolyzed to a simpler carbohydrate. What do I mean by that? Well, monosaccharides have the general formula CnH2nON. So most have somewhere between 3 to 9 carbons. And we're going to be looking at two types, an aldose, which is a monosaccharide that contains an aldehyde, and then ketose. This is a monosaccharide that contains a ketone group. Now, why might that be important? Well, if we think about monosaccharides and the way that they're classified, you can quickly see that it's based on the number of carbons. So a triose would have 3 carbons, a tetrose would have 4, a pentose would have 5, a hexose would have 6. You're probably most familiar with the hexose because that's glucose, C6H12O6. Heptose would have 7, octose would have 8. If we go back to very simple forms of carbohydrates, the simplest molecule we could look at would be something like glyceraldehyde. So this contains a stereocenter, and it exists as a pair of enantiomers. So if we think about the carbon that is the stereocenter, that's carbon 2. Carbon 1 is the aldehyde carbon, because an aldehyde has greater priority than an alcohol. Carbon 2, though, is the compound that actually has 4 different groups bound to carbon. And so if you looked at the structure of this molecule, you would be able to identify the priority, aldehyde first, alcohol second, the CH2OH group as the third priority, and the hydrogen as the fourth priority, and assign that then as R and S. So I want you to take a moment and draw R and S glyceraldehyde. So think about the fact that it is C3, and draw what that molecule looks like, and then assign R and S as the stereocenter. Again, if you need time, pause, and then resume when you're ready to go. A Fischer projection is a two-dimensional representation that shows the configuration of a tetrahedral stereocenter. What do we mean by that? Well, a Fischer projection has horizontal lines that represent the bonds that project forward or up out of the page, and then vertical lines that represent the bonds projecting to the rear. The first and the last carbons in the chain are written in full. All other carbons are indicated by the crossing of bonds. So if you think about the horizontal lines, another way of saying this is that they represent the wedged bonds, and the vertical lines represent the dashed bonds. So if we think about the Fischer projection then of glyceraldehyde, those are shown here. D-glyceraldehyde, notably because it has a stereocenter, has an optical rotation. This is something that we touched on briefly before, but we're going to come back to again. So if you think about R and S and whether they exist as pure enantiomers or a mixture, say for example 50-50 of racemic compounds. If you had a 50-50 mixture, your optical rotation would be 0. Or if you had a mixture that was something other than 50-50, you would observe, right, some degree of rotation depending upon which of the two enantiomers predominated in the mixture. So to practice, I want you to draw the Fischer projections for erythros. So notice if we count carbons, we have 1, 2, 3, 4. So one more carbon than we had for glyceraldehyde, which is the triose. So if you think back to what we were talking about before, right, you should be able to determine how many stereocenters there are, what is the priority of each of the atoms, and then be able to assign R and S. And again, if you need to, just press pause and then resume when you're ready. One of the things that you're going to notice when drawing the Fischer projections for these molecules is that whether the hydroxyl group is on the left or the right has some significance. If the hydroxyl groups are on the left, we refer to that as an L erythros. If the hydroxyl groups are on the right, we refer to that as a D erythros. But it's not all hydroxyl groups, it's a specific hydroxyl group. We're going to start to see if we can observe the pattern for how we know whether it's going to be L or D. What do you think? So according to the convention proposed by Fischer, D monosaccharide is a monosaccharide that when written as a Fischer projection has the hydroxyl, the OH, on its penultimate carbon on the right. What does that mean? Penultimate means the carbon before the last. So it's not the last carbon, it's the second to last carbon. Likewise, an L monosaccharide is a monosaccharide that when written as a Fischer projection has the hydroxyl on the penultimate carbon on the left. So if we think about this then, D erythros is D because it has this hydroxyl group on the right. D threose is also because this hydroxyl group is on the right. D-ribose is because this hydroxyl group is on the right. And 2-deoxy-D-ribose is also because this hydroxyl group is on the right. Some of the most common hexoses that you're going to encounter are D-glucose, D-galactose, and D-glucosamine. These are important compounds to be able to recognize because they are the molecules that are often found both in living organisms but also as a part of metabolic processes. In addition, there are also sugars that can be differentiated. For example, D-glucosamine has an amino group. D-manosamine has that NH2, also on the 2 carbon, but now it's on the left. It's the C2 stereoisomer of D-glucosamine. D-galactosamine, or the C4 stereoisomer of D-glucosamine, and N-acetyl D-glucosamine, where the acetyl group is this carbonyl and then CH3 that's attached to the amine. N-acetyl D-glucosamine is a component of many polysaccharides, including connective tissue like cartilage. We also see it as a component of chitin. This is the hard shell-like exoskeleton of lobsters, crabs, and shrimp. When we think about monosaccharides having hydroxyl and carbonyl groups, they tend to exist as cyclic hemiacetals. You're going to remember that we've talked about hemiacetals and acetals when we were initially studying carbonyl groups. And we've also studied specifically the carbon of the hemiacetals and the acetals. Now in this case, that carbon becomes very important because the anomeric carbon is the hemiacetal carbon of a cyclic form of a monosaccharide. So anomers then are monosaccharides that differ in configuration only at their anomeric carbon. So if you think about drawing the acetal of D-glucose, you're going to take the mechanism that you know for drawing a hemiacetal and then acetals and apply that here. So let's modify this. It's useful to do this. See if you can draw both. Start with the hemiacetal and then see if you can figure out what it would take to draw the acetal. And again, press pause if you need. So what does that look like? Well, if we're drawing the hemiacetal, we're simply going to take our penultimate carbon. This is the carbon that determines whether it's D or L. And we're going to redraw the molecule where literally our carbon chain wraps around, almost forming a six-membered ring. So notice, if I were to take the electrons on this hydroxyl group, and which is my nucleophile, and attack my carbon of the carbonyl, which is my electrophile, and I know that because I can draw resonance, then I would be able to form a bond between the oxygen that's attached to the fifth carbon and the carbonyl, which becomes an alcohol on the first carbon. Notice the orientation of the hydroxyl group being up is from the hydroxyl group attacking the carbonyl from the bottom, pushing the electrons up. Whereas you could also attack as a nucleophile with the electrons from the top, pushing the electrons on the oxygen down, forming an alpha anomeric carbon. So beta is up, alpha is down. Aldopentoses also form cyclic hemiacetals. So the most prevalent forms of D-ribose and other pentoses are what we call furanoses. So if we think about alpha D-ribofuranose or beta 2-deoxy D-ribofuranose, let's dissect those names. So the alpha now refers to the hydroxyl group on the one carbon being in the down position. Ribofuranose refers to the fact that this is a five-membered ring, including the oxygen. Beta 2-deoxy D-ribofuranose means that at the 2 position, there is now no longer a hydroxyl group. Instead, there is a hydrogen. So the prefix deoxy means without oxygen. Now, if we think about D-fructose, which is a 2-keto hexose, it also forms alpha and beta cyclic hemiacetals. So here is alpha D-fructofuranose. If the hydroxyl group functions as a nucleophile, attacks the carbon of the carbonyl, which is the electrophile, it will generate or form either the beta or the alpha, depending upon the orientation of the nucleophilic attack. So notice here, this is alpha D-fructofuranose. Here, this is beta D-fructofuranose. So if we think about drawing the hemiacetal and the acetal of glucose in a chair configuration, it's useful to us to think about what that would look like. For example, the six-membered rings of pyranoses are more accurately represented as their chair conformations. So if we think about a chair of glucose, we can actually still see this anomeric position, where in this case, the hydroxyl group is up, so it would be beta. But if we were to break this bond and rotate and then attack from a different position, we would also be able to form the alpha compound. Notice, the optical rotation for beta D-glucopyranose is not the same as the optical rotation for alpha D-glucopyranose. So it is a misconception to think that beta will always have a specific optical rotation that is matched or mirrored by the alpha. So draw the beta anomer of glucose as both the Hayworth and the chair configuration. And if you need to, take a pause. And if you're not sure what the Hayworth configuration is, think back to when we drew sugars as a six-membered ring, but used the lines instead of wedges and dashes. So here's an example of a Hayworth projection where, notice at the anomeric position, I'm going to say that it's beta D glucopyranose because at the beta position, the hydroxyl group is up. D because my oxygen at the fifth or the penultimate, second to last, carbon is to the right. Notice I could also draw this as the chair configuration. You will become very comfortable interconverting between alpha and beta D-glucopyranose, as well as drawing both the mils, which is the wedges and dashes, the Hayworth, and the chair conformations for sugars. The next thing we want to talk about is the mutarotation of glucose. So one of the key ideas that we've been talking about in organic chemistry is this idea of equilibrium. The challenge with equilibrium is to understand that at any given point in time, reaction conditions or the local environment will favor or contribute to the direction of equilibrium. So in this case, if I had beta D-glucopyranose with a specific optical rotation, in solution, that beta D-glucopyranose can adopt an open chain form, and at that point, it can interconvert between both beta and alpha. So at any given point in solution, I'm going to have certain mixtures of each of these compounds. When we think about the formation of hemiacetals, we're talking about the formation of an anomer. But if we go on to form the full acetal, then that's going to be a glycoside. A glycoside is a carbohydrate in which the OH on the anomeric carbon is replaced by the OR. So again, I'm going from a hemiacetal to an acetal at the anomeric position. The simplest way to do this would simply be by the addition of methanol. If I added methanol, I could form the acetal or a glycosidic bond. Notice I still have my beta and my alpha positions. The glycosidic bond, thus, is going to be the anomeric carbon of the glycoside and an OR group. So to name a glycoside, we're going to name the alkyl or aryl group that's bonded to the oxygen, followed by the name of the carbohydrate. And we replace the ending E by "ide." So for example, methyl beta D glucopyranoside, or methyl alpha D ribofuranocide. Why does this matter? Well, if we think about structures that include carbohydrates, one of the most important are going to be nucleotides. We're going to start to look at nucleotides that are comprised of a phosphate, a sugar, and a base. Here, we show the sugar and a base connected through a beta N glycosidic bond at the aromatic carbon. Why does that matter? Well, if we think about the anomeric carbon of a cyclic hemiacetal, it can react with the amine to form an N-glycoside. In the biological world, the N-glycosides of D-ribose and 2-deoxy-D-ribose with the following heterocyclic aromatic amines comprise our nucleotides. So uracil, cytosine, and thymine are our pyrimidine bases, and then adenine and guanine are our purine bases. So I want you to take a moment. What is the glycosidic bond for a pyrimidine? So choose any pyrimidine other than the one that is shown. In this case, the pyrimidine that is shown would be cytosine. So choose a different pyrimidine and draw the glycosidic bond. Now do the same for a purine, using the examples shown above, where obviously this is a pyrimidine. You need to substitute that pyrimidine with any one of the purines that were given previously. Now, it's important for us to recognize that a carbonyl group can be reduced to a hydroxyl group using a reducing agent such as sodium borohydride. So take a moment and draw the reduction of butanal with sodium borohydride just to refresh your memory. Remember, the addition of hydride is where hydrogen functions as a nucleophile. If I think about the carbonyl group of a monosaccharide being reduced to a hydroxyl group using something like sodium borohydride, one of the most important things is to recognize that all of the other hydroxyl groups won't be affected by a reagent like sodium borohydride. Sodium borohydride is only going to touch the aldehyde. In this case, it's going to add a hydride, generating a primary alcohol, forming D-glucatol or D-sorbitol. We name alditols by replacing the OSE of the name by itol. So sorbitol is found in the plant world in many berries, cherries, plums, pears, apples, and seaweed, and it's about 60% as sweet as sugar and is often used as a sugar substitute. Other common alditols include erythritol, mannitol, and xylitol. A carbonyl group can be oxidized to a carboxylic acid using an oxidizing agent such as chromic acid. Take a moment and draw the oxidation of butanal with chromic acid. If you need to, refer to the Jones oxidation mechanism that we have covered previously as a group. So the aldehyde group can be oxidized to a carboxylic acid. A reducing sugar is any carbohydrate that reacts with an oxidizing agent to form an aldonic acid. Notice here, beta-D-glucopyranose in the form of a hemiacetal has to open to the linear sugar in order for an oxidizing agent in basic solution to form D-gluconate. This is the anion of aldonic acid. If we think about enzyme catalyzed oxidation of the primary alcohol at carbon 6 of a hexose, that can also give a carboxylic acid. So in this case, D-glucuronic acid. If we think about the way we would draw that chair configuration now, instead of having CH2OH, we have a carboxylic acid here at the 6th carbon. So the body uses glucouronic acid to detoxify foreign alcohols and phenols. These compounds then are converted in the liver to glycosides of glucouronic acid, and then they're excreted in the urine. What's interesting is the intravenous anesthetic propofol is converted to the following water-soluble gluconuride and then excreted. So this is an example of the way in which your body uses sugars to make soluble compounds that would otherwise have difficulty being processed and excreted. L-ascorbic acid, or vitamin C, is synthesized both biochemically as well as industrially from D-glucose. Notice the formation of L-ascorbic acid, or vitamin C, requires several iterations. This is an example of a starting material that can then be oxidized to L-dehydroascorbic acid. So both of the compounds are physiologically active and are found in most bodily fluids. Now, can you spot which is the penultimate carbon? There should be something about that penultimate carbon that triggers a question. We'll talk about that later in class. Table sugar, which is obtained from the juice of sugarcane and sugar beet, is an example of a disaccharide. Notice there's a glycosidic bond between the 1 carbon, or the anomeric carbon, of this sugar and the 2 carbon of the sugar. So this is a unit of alpha D-glucopyranose, and this is a unit of beta D-fructofuranose. These are both really important because they form sucrose, which is what we think of as table sugar or baking sugar. It's also the sugar that is frequently found in fruits and sometimes even vegetables, in other types of plant-based compounds. So the principal sugar that's present in milk is lactose. There's about 5 to 8% of lactose in human milk, and about 4 to 5% in cow's milk. And you can see here that the glycosidic bond is now between the 1 carbon, the anomeric carbon, and the 4 carbon. This is what's referred to as a beta 1,4 glycosidic bond. Beta because we're referring to the anomeric position. Maltose is the compound that is found in malt, or the juice of sprouted barley, or other types of cereal grains. Here, this shows an alpha 1,4 glycosidic bond where, again, at the 1 position, the hydroxyl group is down. So alpha 1,4 in the glycosidic bond. Finally, we're going to think about the ways in which we can use sugars as chemical identification or recognition molecules. So the membranes of animal plasma cells have large numbers of relatively small carbohydrates. In the ABO system, individuals are classified according to 4 blood types: A, B, AB, and O. If we think about what these blood types look like at a molecular level, we have our red blood cells. Connected to that red blood cell is N-acetyl D-glucosamine through a beta-1,3 glycosidic linkage to D-galactose, which is connected through an alpha-1,2 glycosidic linkage to L-fucose, which is also connected through an alpha-1,4 glycosidic linkage to N-acetyl D-galactosamine. If you have the N-acetyl D-galactosamine, that's type A. If instead you have D-galactose, that's type B. Can you guess what type O is if I tell you that type O can donate blood to either type A or type B? Starch is another example of a polysaccharide that in this case is used for energy storage in plants. It can be separated into 2 fractions, amylose and amylopectin. Glycogen is the carbohydrate that is used to store energy for animals, so a nonlinear polymer of D-glucose joined by alpha-1,4 and alpha-1,6 glycosidic bonds. If you think about the total amount of glycogen in the body of a well-nourished adult, that's going to be about 350 grams, or about 3/4 of a pound, divided almost equally between liver and muscle. Let's take a moment and take a look at this. So this is an example of starch. It's comprised of, my apologies. This is an example of glycogen, which is comprised of alpha-1,4 and alpha-1,6 glycosidic bonds. I don't think I have a picture of starch. I need to go and find one. I'll have that for class. And then cellulose, which is a linear polymer of D-glucose units that are joined by beta-1,4 glycosidic bonds. It has an average molecular weight of 400,000 compared to approximately the 2,800 D-glucose units per molecule. So both rayon and acetate rayon are made from chemically modified cellulose. Notice here the repeating beta-1,4 glycosidic bonds. Next time we're going to be taking a look at amino acids. Thanks again for your attention. Have a great day.